All right, so your test, mentioned it in an email, but your test will be in two parts. So there's a part that will be open. I think I have it set to open up at 11 o'clock this morning. And that's kind of what I refer to as your take-home part. Wow, that's really thick. No need for that.
For the take-home portion, do you have the same restrictions on using notes and things like that?
No, on the take-home part, you can use your book, you can use your notes. But I still don't want you to use internet, so no Google, no other people. You can still ask me questions, but no internet, no other people. So that part I anticipate being the more, I'll say, the conceptual part. So that'll be the part where you'll have maybe a proof or two on there about different things. That would be where if I ask you to prove something is a vector space, that would be on that particular part. So I know that I had been asked in class if you had to memorize those axioms for the test. No, the answer is no at this point because I'm letting you do it take home and you can use your book. So you can actually go back and make sure that you catch all 10 axioms correctly for that. But proving something's a vector space would be on that section. Proving things are subspaces would be on that section. I'm going to put, if I ask you a question about doing the adjoint, I'll do it on that section as well because I think doing the adjoint of a matrix takes a little bit longer since you have to do all of those. Well, if you have a 3x3 matrix, you have to do 9 determinants to be able to do the adjoint. So in general, that takes a little bit longer, and I don't want that to bog things down. So adjoint would be on that section, those kinds of things. So, but it's the more conceptual side. So the in-class part. So this is no book or notes. And then, of course, no internet, no other people, all those good things. And this is going to be your more computational idea. So this will be I give you a matrix, I ask you to find its determinant by, say, expansion by minors. I guess I should have said that for the other thing with the take-home part, too. I might ask you for the take-home part to do a determinant by row reduction. That would be on the take-home part. So in-class part, we would be looking at like expansion by minors. Oops, there's not two S's in minors. That would be certainly something I would expect you to do. This would also be, there would be a few true-false questions. Actually, there are 5 true-false questions. I'll just tell you that there are 5 right now to start with. Let's see, what else? This might be doing some computations with your properties of determinants. So what I mean by that is, of course, that if you have determinant of a product, it's the product of the determinants. Determinant of an inverse is 1 over the determinant. Determinant of the transpose is the same as the determinant of the original. If you have a constant times the matrix, remember that when you multiply a row by a constant, it changes the determinant by that factor. So if you have an n by n matrix, then when you pull out the constant, it gets multiplied by itself c times. So those are the kinds of properties I might ask you to do things with. So you'll be given a determinant value, or you'll have computed a determinant value and then maybe use that determinant value to find other determinants. But again, it's all going to be computational. So it's just basically a way to make sure you understand these properties. So not long computations. So like if I say that determinant of A is 7, then you would say determinant of inverse of A is 1/7. I mean, it's not long problems. It's just that making sure that you remember these properties. Checking linear independence and span. So what I mean by that is I could give you a set of vectors. You check by row reducing whether or not that set's linearly independent, whether or not it spans. So then you also, along those same lines, whether or not it's a basis. I might also ask you, give you a set of vectors and ask you to expand it to form a basis for a vector space. So that's the ones where, like we talked about last time, where maybe I give you a couple of vectors and then you add on the standard basis for the vector space and row reduce and pick out the ones that you need. We did those last time. And then also we talked about reducing a spanning set to a basis, which is really, honestly, is what you do in the previous thing too. I mean, when I say you expand a set to form a basis, really what you're doing is you throw in the standard basis, so you're creating a spanning set and then throwing out the ones you don't need. I mean, literally these two things are essentially the same thing. And then another computational kind of question that I might ask you is, if you have a basis, or once you've found a basis, can you write a vector as a linear combination of a vector as a linear combination of the basis vectors? And that is, again, coordinates with respect to a basis. And again, that just amounts to putting in a matrix and row reducing. And then the last thing I might ask you is determine the dimension. But again, that's just a matter of find a basis and count how many elements are actually in the basis. So again, very computational, very calculator active, minus the being able to do a determinant by expansion by minors. I anticipate that much of what you're going to do on the test, the in-class portion of your test, will be using your calculator to do the matrix operations, mainly the row reduction, and then using that answer to give your interpretation, to be able to write the answer, right? Because when you check linear independence and span, for linear independence, you look for a pivot in every column. For span, you look for a pivot in every row. Okay, so that's, again, putting the matrix, row reducing, and interpreting your answer. Expanding a set to form a basis, that's put your vectors in columns, add on the standard basis, row reduce, pick out the things that correspond to pivots. That's, again, doing row reduction. Same thing for reducing a spanning set to form a basis. Same thing for finding coordinates with respect to a basis. That's, again, putting the vectors in your basis in a matrix, then putting the vector that you want the coordinates with respect to as the augmented part, and row reducing and writing down the solution. So this is a very, very calculator active portion of the test, making sure that you know how to row reduce and then interpret the answer that you're getting. Is that the kind of information you wanted?
Yes, thank you.
Yep, you're welcome. Happy to help. Any other questions at all?
Did you say when the in-class portion was going to open up?
So the in-class portion, let me go back up here to the top. So your take-home portion should open at 11 today. And it's due at 5 p.m. on Friday. The in-class person opens at 8:45 on Friday. So this is all on Friday. Opens at 8:45 and it's due at 10:15. Now I don't anticipate this to take you longer than an hour at all. I don't think it should at all. If you know what you're doing with your calculator and know how to do the interpretations things, I don't think it's going to take you an hour. But I want to give you the buffer time to be able to get it open, get the test open, make sure you write down the statement at the beginning, and then also have time to snap pictures of your work and get it uploaded into Moodle. That's why I've got that basically a 30-minute buffer time there for opening it at 8:45 and do it 10:15. Do those times work for everybody, by the way?
Yes.
Yeah?
Yeah.
Okay. Cool. All right. So, and I will be on Zoom as well if you've got questions on the exam as you're taking it. I'll be on Zoom during our normal time. I will have to cut out probably around 5 till because I have to start my 10 o'clock class at 10, obviously. So, but if you've got a question or something along those lines while you're taking it, you can go ahead and ask it. I will have my speakers up so I can hear you. What I would do is encourage you to have your speaker muted unless you're going to ask me something, because if somebody else asks a question, then it might interrupt you as you're working. So, or you could just log into Zoom if you've got a question that way too. Whichever way you want to do it. I'm just trying to give tips. It's the first time I've given a test through Zoom, so this is new to me too.
So for the in-class portion, we're going to be writing everything down on paper and then, like, uploading it to Moodle?
That is my plan, yes.
Okay.
Any other questions at all? And of course, you're welcome to ask me questions about the take-home as well, if you've got questions about that. So, all right. Well, let's get started on some new stuff. Let me see if I can highlight some stuff and make it go away. All right. So let's talk about these concepts that I introduced in the video that I asked you to watch for today, which is basically a combination of sections 5.5 and 5.6 in your text. These ideas of row space, column space, null space, and rank and nullity all go together. So basically I'm combining the two sections together to make one lecture, if you will. Pardon me. So, as mentioned in the video, your row space, so if you've got an m by n matrix, your row space is the span of the row vectors of A. So what we mean by that is if I think of A as m row vectors, then the row space of A is just all possible linear combinations that you can make from the rows. So that's all we mean by that. So we treat the rows as individual vectors and take all the possible linear combinations and that's what we get. But whatever set we get, that's what we mean by the row space. Now, just to mention this again, I've mentioned it on the video, but to mention it again here, when I think about these rows going across the columns, that means that each of these vectors has n components to it because we have n columns as we go across. So the row space is always going to be a subspace of Rn. All right, so then your column space, same idea. This is the span of the column vectors. So again, we think of the vectors as columns in the matrix, or I said that backwards. We think of the columns as vectors, and we do the set of all linear combinations of the columns. I probably shouldn't use a C here since I'm using C's for the letters for the variable, the vectors, I mean. Oops, there should be an M up here. All right. So again, we just say take all your columns, take all possible linear combinations. That's your column space. As vectors, your columns go down the rows. So there's going to be m components in your column vectors. So this is going to be a subspace of Rm. Your null space is, this is the set of solutions to the equation ax equals 0. We've done this since the beginning of the semester. We've solved systems of linear equations that are homogeneous, having 0 on the right-hand side. So all we're doing is giving it a name now, calling it the null space. We've already noticed that this set of solutions can be written as a linear combination, right? Because we've talked about how to write it as a parameter times a vector plus another parameter times a vector and so on down the line, where those parameters come from the free variables. So we've already talked about how we can write the set of solutions to the homogeneous equation as a linear combination of a set of vectors. So it's not a huge surprise that it's also going to be some sort of a space here. One thing that we notice here is that, of course, if I take my matrix A and I multiply it by x, so this is an m by n, so this x has to be n by 1 to be able to multiply. Your x, whatever I'm plugging in here, is the solution, so these vectors that are in the null space also have to be in Rn. So the null space of A is a subspace of Rn. Okay, so just looking at the three spaces again, the row and the null space are subsets of Rn. The column space is a subset of Rm. The row space and the row space and the null space being subspaces of the same Rn is going to pop up in the next chapter. That's why I'm making a bigger deal out of it than it seems like it needs to be. This is going to pop up again in the next chapter for one of the concepts that we're going to do. All right. Rank. Rank is an easy concept. So this is just the number of pivots in the reduced row echelon form of A. Whereas the nullity is the number of free variables in the reduced row echelon form of A. Now, I should write this as pivotless columns, but that's okay. I think we know what I mean. All right. So why do we care about these kinds of things? So let's talk about some reasons why we care about column space and null space to start with. All right, so one thing that we notice is, say we're trying to solve a system of equations. So say we're trying to solve the system AX equals B. Well, when we do this, if I think about what happens when we multiply an A times an X. So let me write it this way. Say I have a column 1, a column 2, a column n, and I want to multiply this by the vector x1, x2, xn. Notice that when we do this multiplication, this column only ever gets matched up with that top number in the vector x, right? When I match up row to column for my multiplication, the only things that ever get multiplied by the x are the C1. The only thing that gets multiplied by the x2 are the elements in C2, and so on down the line. So when you do this multiplication, you get a linear combination of the columns. Right? When we do our entries, when we do, say, the first entry, we would take the first row times the vector. Well, the only thing that ever gets multiplied by the x1 is the first entry in C1. When we go to the second one, we would take the second row and multiply it times the vector. But again, the only thing that gets multiplied by the x1 is the second entry in C1, and so on down the line. So when you do this product, you get a linear combination of the columns. So what this has to do with consistency is then, if I'm supposed to plug in a number, or excuse me, if I'm supposed to plug in a vector here for x and get out b, b has to be a linear combination of the columns. So we get that this system is consistent if and only if B is in the column space of A. Okay, so the only way that's what has to happen. So we can think of B then as a vector that's in some vector space. It's in a column space here in this particular case. So that's what column space has to do with a little bit with the solving systems of linear equations. So let's focus a little bit more on that. So the theorem that we're going to prove here, which is it's not a bad proof, but here's the theorem we're going to prove. So we're going to look at the solutions of AX equals B. What it says is, let this x sub p be a solution. So one fixed solution for the system AX equals B. Then every solution to the system can be written as that particular solution plus some solution to the homogeneous system. Now, we've done this before when we've written split it up into vector form. Remember, we had basically a fixed vector and then a piece that had some parameters in it. So let me do that as an example before I talk about the example that I typed. So let's say you had a reduced row echelon form that looked like the following. Let's say this was my reduced row echelon form of my system of linear equations after I row reduced. I see that we have two free variables, right? We've got one here and we've got one here. So that I would have my x4 would be t and my x2 would be s. Those would be my parameters. My x3 would be -3 minus 4t when we subtract that 4 to the other side. And my x1 would be 5 minus 3s plus 2t when we moved these two things to the other side. And then if we write this in vector form, we can write the constant parts out first. We would have 5, 0, negative 3, 0. And then plus s times negative 3, 1, 0, 0. And plus t times 2, 0, negative 4, 1. So what this is an illustration of the theorem. This would be your x sub p. This is one solution to the system of linear equations. And you can check that pretty easily just by putting in 0 for s and for t over here, right? If I put in 0 for s and 0 for t, I get 5, 0, negative 3, 0. So this is one particular solution to ax equals b. This part here represents that homogeneous solution. If I put any vector in this form and multiply it by a, I will get 0. So this is how we're writing all of the solutions. Every single solution to this system can be written as one particular solution plus all of the homogeneous solutions. Okay? We've already seen this. We've done this before. We just haven't called it this before. But this is exactly what we've done before since we've been solving these systems of equations, right? We found this form and then split it into vector form. This is the reason why we were playing around splitting it with the vector form. All right? Well, let's see how this applies to this other example, because this is one of the main reasons why we worry about these kinds of things, and it has this application to differential equations. So you can check pretty quickly that this solution, or this equation, this function satisfies this equation. It's not too hard to do. You use the product rule and then subtract off what you get. You do get e to the x. So you can check that this is a particular solution. That's why we use x sub p. This is a particular solution to this differential equation. You can also check that this is a general solution to the differential equation where I've replaced the e to the x with a 0. So notice this is the associated homogeneous equation. This is non-homogeneous because I have a function that's other than 0 on the right-hand side. But I've got the particular solution here. I've got the homogeneous solution here. So that tells me that I know that every single solution looks like this, a particular plus the general for the homogeneous. If you're taking differential equations or going to take differential equations, this is how you do solving non-homogeneous equations typically. You find the general solution to the homogeneous, and then you go find a particular one and use this result from linear algebra to get the whole solution. Okay. Ignoring the differential equations part, especially if you're not interested and haven't seen it at all, does this part up here make sense what I'm trying to say as far as a result from the theorem with getting the solutions to the system written down? That okay with everybody?
Yeah.
Yeah? Okay. All right, so let's talk about how the proof would go. So we need to start, we say that we can write a solution with, in terms of a particular one and then the associated homogeneous one. So the way we do this is we're going to say we have x sub p is a fixed solution. So this is our one particular solution. And we'll let x represent any other solution. then it's not too hard to check that if I take A and I multiply it by x minus xp, well, I can distribute over the difference. Now remember, we're saying that these are solutions to the original equation, the ax equals b. So both of these have to be equal to b. So I get the 0 vector. All right, so what this tells us is that this x minus xp is a solution to the associated homogeneous system, the ax equals 0. Because when I took the x minus xp and multiplied it by a, I got 0. And now we are pretty much done, because remember the result said I can write any other solution as a particular one plus the homogeneous one. Well, it's not too hard to see that this arbitrary solution now is xp plus x minus xp. This is your x of h. So I have that any solution can be written as a particular solution plus a solution to the homogeneous system. Now, as far as the solution to the homogeneous system, of course, is that this homogeneous thing is in the null space. So just to go a little bit further and see why we get things that look like this general solution here, or scrolling back up over here, this general solution here, let's see why that's the case. Well, certainly with our knowledge of null spaces, if we let's say, I'll call them V, V1, V2, out to V sub K, be a basis for the null space of A, then this x sub h is some linear combination of the v's. Okay. So now we have that our arbitrary solution, the x, can be written as that one fixed solution. Notice we said that let that x sub p be a fixed solution, plus some linear combination of the null space basis vectors. Which is exactly what we were doing back in chapter 1 when we were rewriting the solution to the system of equations as a fixed vector plus a linear combination, an arbitrary linear combination of some other vectors. But the whole point of this theorem is that when you're trying to solve a non-homogeneous system, you can reduce it to solving the homogeneous system and then finding a solution. Now, you don't have to find infinitely many. You can just find a solution that works and then add the two together, and that gives you your arbitrary solution in general. Now, for our purposes, we've already been doing this, so this seems like not a very interesting result, because we've already been doing this when we've been solving systems of linear equations. But it does matter when you're not just talking about solving systems of linear equations, but solving things like differential equations, right? When we do solution spaces of differential equations, those are vector spaces. So we're interested in trying to find what generates the whole vector space, if you will. And so this is going to be generating all of those solutions for us. I shouldn't say that this is a vector space because we have issues with a zero vector, but the homogeneous system definitely is a vector space piece. But anyway, I know I've probably harped on this a little bit more than I needed to, but this is the reason why we care about this particular result. Because when we're trying to search for solutions, typically it's easier to find solutions to the homogeneous system. So use that piece to give us our general piece, and then go and just find one solution to the non-homogeneous piece. That's typically harder, so we work hard to get the one solution and then add them together to get our final solution. Questions on that at all? Really the main thing I want you to get out of this is we've already been doing it. We see that particular piece here, we see that particular piece here, and we see that homogeneous piece here. Any questions on that at all? Are we okay with that? Oh, hearing silence, I'll either take that as a yes or everyone's just in shock, one of the two.
I'm just captured by its beauty.
Yes, exactly. All right, so let's see how this goes with this particular example that has to do with linear algebra. So here's a big system of linear equations. I chose not to try to type this matrix in because I didn't really want to since it's a 4x6 system here. All right, and I'm also going to refer to this example later. So here's a system of linear equations. We can think about the augment bar going right here. All right, so notice that we have free variables here and here and here. If I ignore those for the time being, or just think about these as being parameters where I've set them equal to 0, this would tell me that x1 equals -1, x3 equals -5, and x4 equals -2. So in this particular one, our xp would be -1 for the x1. I said think about the parameter being 0 to start with, so x2 would be 0, x3 would be -5, x4 would be -2, and then x5 and x6 would both be 0. That's our particular solution. So the reason why I've got zeros in the 2, the 5, and the 6 spots is because those are where our free variables are, and I said treat those like they're 0 right now. So this would represent our x sub p. Our x sub h would be the pieces where we ignore the particular part and just worry about the free variables. So if I think about these being 0 on the right-hand side here, then I can move these pieces over to the other side. Oops, I need my parameter. I need a parameter for x2. I need a parameter for x5, and I need a parameter for x6. So x2 would have a 1 here, and it would have zeros for 5 and 6, right? x5 would have a 1 here, and zeros for 2 and 6, and then t would have a 1 here, and zeros for 2 and 5. By the way, this is how I know that these particular vectors are linearly independent. I can't possibly get a 1 here using the zeros here. I can't get a 1 here using the zeros here, and I can't get a 1 here using the zeros here. I really do see the identity matrix right there before I fill anything else in. So when we're doing this, we see why we get a basis for the null space, because it definitely is linearly independent. Now to fill in the rest, across your x1, when we subtract over, this will be a -3 here, this will be a -1 here, and this will be a +2 here, just flipping the signs over. This first one has nothing here, and has a 1 here, and a -1 here. This has nothing here. This has -4 here, and -2 here. So this is our homogeneous part. I know I filled that in a little differently than I would have otherwise that we talked in the past, but I was just trying to emphasize individual pieces. But again, we see the particular solution and the homogeneous solution out of this. Questions on this at all? All right. So let me scroll here to the next page. All right, so I want to use the same thing as my example. Same exact matrix that we had. I probably didn't want the constants on the end, but we'll see what I... actually, yeah, let's go ahead and just delete these constants out. I don't care about those in this particular example. So let's think about the first question. So what effect do elementary row operations have on the null space or on the row space of a matrix? Well, remember the null space is the set of solutions to AX equals 0, right? So the null space of A, again, is the set of solutions to AX equals 0. Well, how do we solve this? Well, we take the original matrix and we row reduce it. And then we write the solutions to the row reduced matrix. Well, that means that if we do elementary row operations on the original matrix, it must not change the set of solutions to the null space because we use the reduced row echelon form to write down the solutions, right? So it must be the case. Otherwise, what we've been doing all semester is wrong. It must be the case that elementary row operations do not change the null space. That's operation, not operators. Now let's think about why that's true. I start with a solution to the original equation, AX equals 0. Remember, one of the ways that we can accomplish elementary row operations is by doing multiplication by an elementary matrix, right? So if I want to row reduce A, I can multiply it by a whole bunch of elementary matrices, and I still get 0 on the right-hand side because if I take this matrix times the 0 vector, I'm going to get 0. And so then I just get down to whatever that particular thing was, right? The whole idea was row reducing this thing until we get down to the identity matrix. Notice it doesn't change the right-hand side at all. So whatever solutions I get at the end, I don't know why I wrote this here. Let me erase that. Whatever we get at the end here is going to be the reduced row echelon form of the matrix, right? This is going to be the reduced row echelon form of the matrix, so I can write down the solutions from there, and I didn't change anything. If I have a solution here, these are all invertible, so I can go back up to the original, and I have a solution here. Either way, if this is your reduced row echelon form here, I don't know it's the identity matrix because in particular it doesn't have to be square. But if this is my reduced row echelon form here, if I have a solution in my reduced row echelon form, elementary matrices are all invertible, so I can get backwards up to here. So if I start with a solution in the reduced row echelon form, I get a solution to the original. So that's why elementary row operations don't change the null space. The same thing ends up being true for the row space of a matrix. When we do elementary row operations for with the row space, they also don't change the row space at all. The reason for this is instead of thinking of it as a product of elementary matrices, just think about it from how you do row reduction. You either swap your rows, you multiply a row by a constant, or you multiply a row by a constant and then add it to another row and replace the other row. All you're doing when you row reduce is doing linear combinations of the rows. So all you're doing when you do row reduction is just replacing certain vectors by linear combinations of other vectors. Well, all you're doing, remember, the row space is the set of all linear combinations. So you didn't do anything to the row space. It's just you just replaced certain vectors with other ones, but they were linear combinations of the original. So you end up with the exact same set that you would have started with. So elementary row operations don't change the row space and they don't change the null space, but they do change the column space. And the easy way to see that is, say I had the matrix 1, 2, and 2, 4. Then the column space here, this is the last thing I'll talk about today, and we'll do more of this on Monday. This would be a constant times the first column plus a constant times the second column. So a linear combination of the columns. If I row reduce this, I get this, right? Can I get 1, 2, 0, 0 from this set? Well, the only way I'm going to end up getting, well, to get 0, 0 out of this, well, let's talk about it the other way. Can I get one vector that's in this particular space is 1, 2. Can I get a 2 in the lower component here for a vector? If I use 1, 0 and 2, 0, can I possibly get a 2 out? I can't, right? If I try to do a linear combination of these two columns, I cannot get either of those. Okay? So my column space changes. So the column space of A changes when we row reduce. All right, so one of the things that we're going to be interested in doing on Monday is finding bases for these particular spaces. Now, we've already done the null space, so we're going to concentrate on finding bases for row space and column space. So we'll talk about this on Monday. But the whole point is that you still want to do row reduce, and you still want to read the answers from your reduced row echelon form. You just have to be careful about which vectors you go and pick. So we'll talk about that on Monday. Again, your take-home test should open at 10. Sorry, it should open at 11, I think is what time I set it to open. But any questions at all before we go? All right. Well, we'll talk to you all later. Have a good one.
Thank you.
Yep, bye-bye. Save it out here.